Laguerre polynomial. Okay. This is also a special function, okay, and we are going to just look into one particular point on this solution of Laguerre differential equation. That's it. Okay, that's the topic for today. Okay, let's see how we can do it. It's something similar to yesterday's class, okay, and we are going to derive it in a similar way. We are going to look into the power series, okay. So let's first write down how does the differential equation pattern looks like for this, okay. So the differential equation here is x t square y tx square. Let me shift to a black pen. I think darker is better. Plus 1 minus x dy dx plus n times y is equal to 0. So let's just mark this as 1, okay, and this is something which is known as the Laguerre equation, okay. So is known as Laguerre differential equation. Okay, so this is Laguerre differential equation. Now for this, just like yesterday, we actually have to define a power series, and we are going to take a power series just like the trial expression or the trial solutions that we take. It's a similar approach here, okay. R is equal to 0 to infinity, and this would be something which is similar, a to the power r x to the power k plus r. So this is something which we have taken yesterday also. We're just going to look into this, okay. We're going to see that how does this equation give you the result to this solution, okay. So be the series solution, be the series solution, okay. So let's try this now, okay. Equation 1 we have to modify accordingly, okay. Or maybe you can just write down here series solution of equation 1. So let's just follow the steps here. Dy by dx is equal to summation r is equal to 0 to infinity ar k plus r into x to the power k plus r minus 1, right. So let's just mark this as number 3. So in a similar way we can also find out what is d2y dx square, and that would be summation r is equal to 0 to infinity ar k plus r, then k plus r minus 1 x to the power k plus r minus 2, right. So if we differentiate that, we should get this. So this is 4. So now just like yesterday, using 2, 3 and 4 in 1 implies, right. So let's just use whatever expression we have. We can take x into d square by dx square. So maybe I can just write it down. R is equal to 0 to infinity. This is ar k plus r and then this would be k plus r minus 1 x to the power k plus r minus 2, right? And then we can write down this as plus 1 minus x. I would suggest all of you, when you write down in your exam also, at least do it in detail. Important, don't make mistakes at the same time, you score better. This would be a r k plus r x to the power k plus r minus 1, right, plus n summation r is equal to 0 to infinity a r x to the power k plus r is equal to 0. Okay, so now we are going to just adjust these x that we have, right? So let's just do it. So this one can be written as summation r is equal to 0 to infinity a r k plus r, this is k plus r minus 1 into x to the power k plus r minus 1, because there is one x, power is 1, minus 2 plus 1, so it will be minus 1, right? And then similarly what we can do here is we can just separate them out here. Okay, we'll see that there will be two k plus r terms here, right? So in this one I can take 1 into this, so this will be summation r is equal to 0 to infinity, and this would be a r k plus r x to the power k plus r minus 1, right? So what you can do is I will just take this x to the power k plus r minus 1 outside, because we have it here and here also, right? So we'll do it that way. I think that will be one step I have gone ahead. Okay, so keep this. Then we have got the next term, which is, this is x, and this is k plus r minus 1, so the power will get cancelled out, so I'll have just x to the power k plus r. So here also we are going to do the same thing, right? So I'm just going to take it and let's keep it inside bracket. This is summation r is equal to 0 to infinity a r k plus r. Okay, and there's a minus sign here, so what you can do is we can take this minus outside. Okay, let's write it down directly. We can take this minus here, and then this is x to the power k plus r, because this x and that minus 1 will get cancelled out, and we have got x to the power k plus r here, n into ar, right? So we can just write it down this also. So we can just write it down as minus of n. Okay, and both the equations we have got ar common. In fact, here also ar is common, right? So we can even take this ar outside, but anyway we can do it in the next step, not a problem. Let me write it down here only. Ar into x to the power k plus r is equal to 0. Okay, so we have it here. Now here also what we can do is okay, let me just go to the next slide. Maybe I can just copy this down, or I'll do it here only, have some space at the bottom. So here what you can do is this. Okay, implies ar I can take it out, not a problem, and then I can actually summation ar, in fact we can just take it out, right? Summation we can do it later, it's the same thing, it's over ar. So I will take this and make it a bit more simplified. Summation ar, fine. Inside bracket you see this is k plus r, k plus r, so we can multiply both of them, and actually I can get this as k plus r whole square, and then we can multiply k plus r with minus 1, so that means this will be minus of k plus r, just adjustments, plus ar I've already taken out, summation I've already taken out, so I can just write it down as plus of k plus r. That's it, and then I have got this x to the power k plus r minus 1. Okay, so that's the term that we have. In a similar way here also I can take out AR common, so I take this minus summation AR, and within bracket it would be K plus R minus N x to the power K plus R is equal to 0, right? And we can see that this K plus R and this K plus R will cancel out, so we are actually getting some simplified terms here. Okay, so we have just written this, so let's just write down this again in the next page. Okay, we'll write it down in simpler way. Just write it down here. So summation R is equal to 0 to infinity AR K plus R whole square, okay, into x to the power K plus R minus 1 minus summation minus R is equal to 0 to infinity AR K plus R minus N x to the power K plus R. So yesterday when we were actually solving on the polynomial, the Hermite polynomial, we have seen that we were actually finding out the different coefficients, and in fact we are getting a relation between a higher power of x and a lower power of x. Here also we are actually going to do the same thing. So if we take that approach, we can just start with x to the power K minus 1. So equating the coefficient of x to the power K minus 1, okay, to 0 by putting R is equal to 0. So if you put R is equal to 0, we get this K minus 1 coefficient here. So we can simply write it down as A naught into K square, okay, A naught into K square, because R is 0, so it is K square, and we're equating the coefficient of x to the power K minus 1, okay. So this is equal to 0, okay. Now this will actually imply, okay, A naught is basically a coefficient which is constant, and this cannot be equal to 0, okay. Therefore we can say that K square is equal to 0 implies K is equal to 0. This is a very important result, okay, because later on we are going to see, we are going to get the terms in terms of a0, a1 and so on. So if a0 is 0, everything becomes 0. So I'm basically going to get, not going to get the series here. So this is something which we can mark as equation 6, let's say, okay. So we can mark this as equation 5. I think we have written up to 4, okay. So we have got the result for K, which is actually 0. And then in a similar way we can actually say this, equating the coefficient of x to the power K plus R minus 1 to 0, okay. Here we can actually get both the terms. For the first term, it is K plus R minus 1, so I don't need to do any kind of adjustments. I can just simply write it down as AR and then K plus R whole square. But what about this? Here if I want to get K plus R minus 1, that means this R goes from 0 to infinity. I'll get one term where I can put R is equal to R minus 1, okay, and then there I can actually get these terms, okay. So here what we can do is R is equal to R minus 1, that means I can write minus, and this would be A R minus 1. In place of R we'll put R minus 1, and within bracket it would be K plus R minus 1 minus N is equal to 0, okay. So that's there, and from here I can easily find out the relation between AR and AR minus 1. So what is my AR? AR is equal to K plus R minus 1 minus N, okay, into AR minus 1 divided by K plus R whole square. Very important. This is the one that we need, because we can use this relation for finding out all the coefficients, okay. So we know the value of k already, so we can say that put k is equal to 0. This will actually imply that AR is equal to k is 0, so this is r minus 1 minus n, and at the bottom it is r square into AR minus 1, right? So we can actually use this relation, okay? It becomes simpler. Okay. We can in fact take out this minus sign also, and then we can just write it down as n plus 1 minus r, but anyway we're not going to do it right now. We are interested now for finding out the different values or different coefficients a. Let's do it. Okay, we have the relation now. I think we can easily do it. So what we are going to do is now we are going to put the different values of r. So we have already found out k value, so it becomes easy. So let's put r is equal to 1. So if we put r is equal to 1, I can find out what is a1. A1 is equal to, so if r is equal to 1, 1 minus 1 will get 0, and this will be minus n. So a1 would be minus of n divided by r square. So r is 1, so it is 1 here, 1 square, we'll write it down, and this is 1 minus 1, which is 0, so I can write it down as a0. So r1 a1 is in terms of a0. Then we can actually find out r is equal to 2, so this would be a2, and this would be minus, r is 2, so 2 minus 1 is minus 1. I can take out the minus outside, okay, and so this would be, so this is 2 minus 1 is 1, right? 1 minus n, so if I take n minus sign outside, I can write it down as n minus 1 divided by, at the bottom it would be 2 square, and then a0 or a1, right? A1 I can write it down because 2 minus 1, then I can write down the n0 term. So this is minus and minus, this will become plus. A1 I'm going to replace, so this will become plus. So this would be n into n minus 1 divided by 1 square, 2 square into n0. We have replaced a1 by this. So in this way we can actually continue, and we can actually get for r3 also. Okay, so if you check for r3, put r is equal to 3, you get your a3 as, so plus minus minus plus, so it will be minus next term. Okay, and you are going to get n minus 1, n minus 2. So if this is 2, we are getting up to n minus 1 term. If this is 3, we are going to get up to n minus 2 term, right? That's logical. If this is 2, we are getting up to 2 square. So if this is 3, we are getting up to 3 square. So 1 square, 2 square, 3 square, a0. So a0 is common everywhere. So that's the reason that I cannot have a0 as 0, because if a0 is 0, everything else will become 0. Okay, and so on. So we can just keep on doing this, and we can actually write down the final series. So if we actually have the series 2 from 2, yesterday also we did something similar, but yesterday we have seen that all the odd terms are vanishing in Harmite polynomial. A1, A3 and all will vanish out. A4, A2, A4, A0 will survive. Here we are actually having everything. So y is equal to summation r is equal to 0 to infinity, and that was our series. If you remember, this is ar x to the power k plus r. Now k is 0, so that means it will be just x to the power r. Okay, for k is equal to 0. So this is the case that we have. Right now what we can do is we can actually write down the series. So that means we can actually expand this. Okay, so let's expand this. So let me write it down again quickly. Y is equal to summation r is equal to 0 to infinity ar x to the power r. So if I just want to expand it, this would be a0 x 1, right, plus, or sorry, x0, r is starting from 0, plus a1 x1 plus a2 x2 and so on, right? So we can actually just replace the values, and we see that a0 is common to everything, so I'll just take a0. The first relation is x to the power 0, so that's 1. Then a1 is in minus, so it is n square by 1 square. So I'll write it down as n square by 1 square. In the process, we should not forget this x, so I'll just write down x. Then plus the next term, if you remember, a2 is n into n minus 1 divided by 1 square, 2 square into
So
x
A1 equals to
square.
we get minus n a naught.
Uh-huh.
A1 equals to get minus n a naught. N is first.
Uh, did I miss something? Let me check. We have got minus n divided by 1 square, right? What I've written here. It is minus, okay, n, only n, right? That is not n square, obviously. Okay, this is n into n minus 1 and so on. Okay, I think this is correct now. Okay, so minus plus, and then there is a minus here, and then you can keep on writing n minus 1, n minus 2 divided by 1 square, 2 square, 3 square, x cubed plus, and so on. So I more or less have it here. Okay, and now what happens is I have to, yesterday we said that a naught we have taken 2 to the power n. Here for for Laguerre series, sorry, we have to take a naught is equal to 1. If we take that, we actually get that series. Okay, then y is known as Laguerre polynomial. Okay, y is the, okay, so we're going to have the series now. So therefore this polynomial is denoted as lnx, okay, is equal to a naught is 1, so we'll take it as 1 minus yesterday also we did a similar technique. Let's try doing this now again. Okay, so we can write it down as 1 n into n minus 1 factorial divided by 1 square. N minus 1 factorial was never there, so we have to divide it by n minus 1 factorial. Then I will take plus, and this would be n into n minus 1 into n minus 2 factorial divided by 1 square, 2 square, n minus 2 factorial, and then minus, and then so on. Let me not write down more term. You actually should write down the third term also, but I'm just doing it now. So if we just look into it, we can actually write it down in the summation form. So let's just directly write it down. So r is equal to 0. Now this actually can go up to infinity if you could check. So let's see how. This is minus plus, alternate minus and plus are there. So that means that obviously I should have a term of minus 1 to the power r. First term would be plus. And then we have got this entire term is n factorial. N into n minus 1 factorial is n factorial. So I'll write it down as n factorial. There is no, series of n here. It's a series of r. So then I have got, sorry, I missed out x. So this is the second term, which is x. Third term, which is x square, and so on. So then this would be nothing but x to the power r. 0, it will be 1. 1 x to the power 1 square, x square, and so on. And that the denominator we have got this one is we can also write it down as r square, 0 square, okay, not 0 square, sorry, this is r factorial square. This is 1. Okay, this modification I think we should do it here. Okay, um, or maybe I don't need to write down an extra line, but you will hopefully understand this. This 1 square can be written as 1 factorial, okay, square. Okay, that's easy. And if I write down this 1 square into 2 square, you can write down it as 2 factorial, and then you square it. Similarly, the next term would be 3 factorial, and then you square it. Okay, so you can check this, you're going to get this result. So if that's the case, it means that you can write down this as r factorial square. So if I put 0, so 0 factorial is 1, so this is okay. Then 1 square, then 2 square, and so on. Okay, so you'll get this term. and then finally I have got n minus 1, n minus 0, okay, and then at the top there will be an n factorial because of this, and that will cancel out, I'll get back 1, then n minus 1, n minus 2, and so on. So this can be written as n minus r factorial. This is our ln x. So that's it, okay, that's the Laguerre polynomial we have got. So this is important. Again, I don't strongly suggest that you remember this, because so many things to remember, it will become a very big challenge.